Our final speaker is Stefan Vollgger from Geosciences. Stefan was born in Austria, surrounded by the Alps, and perhaps being surrounded by all these rocks and mountains is what led to his decision to become a geologist. Stefan actually started out in mechanical engineering and business economics before realising that he wanted to work outdoors in nature and moved into geosciences. While studying his Bachelor and Masters of Science, he actually worked as a mining and geology consultant, but before he got used to the salary associated with the mining industry, he began his PhD here at Monash, starting in 2011. Stefan's work focuses on structural geology and 3D geomodelling and has taken him to every continent in the world apart from Antarctica, and I believe he's pretty keen to get there as well. During his visit to Peru, he found out that everyone there likes to get a PhD. That's because they use PhD to mean Pizza Hut delivery. Before we get into our pizza, let's hear about unfolding future resources in Screwedup rocks. Thanks, Stefan.
Thank you very much, Kay. Today I want to talk to you about unfolding future resources in Screwedup rocks. So let's start with resources. What are resources? Generally speaking, resources are just supplies from which benefit is produced. And on this planet right now there are about 7.2 billion people living, and this rate is growing by about 100,000 people every day. So to sustain the daily life and the life you're used to, we need to mine and we need to get additional resources. And we use these resources to build houses where we live in, to build universities where we can go and study. We also need these resources to actually use different modes of transportation to build cars and aeroplanes. And we also need these resources for the daily tools and electronic devices we use every day. So to manufacture all this, we need a big pile of different elements and commodities. And these elements have to be sourced from somewhere, and we source them, of course, from the Earth. So let's talk about the abundance of all these elements in the Earth crust. And in this graph, you can see the abundance of some major elements which are very important for manufacturing. From the left side, we can see there is silicon and aluminum and iron. It's quite a lot around. It's about 460,000 ppms, so it's a lot. If we go further to the right side, we can see there are some elements which are where we have a very low abundance in the Earth's crust. And this means that metals like copper, which are very important for electronic devices, or lead, which is still used in a lot of batteries in every car, and gold, they have to be enriched somehow in the Earth's crust. For example, if you take the abundance of gold, it's only 3 milligrams per ton in an average Earth crust. If we would put this average Earth crust into the biggest haul truck in the world, which has a payload of about 363 tons, we would only have a tiny speck of gold in this haul truck. It's about 1.1 grams. So we need to find some processes to enrich the Earth crust in all these elements. But before I talk about these processes, I want to explain you how the structure of the Earth, it's actually similar to an onion. We have different layers, and from the outermost layer to the core, it's about 6,370 kilometers. So it would take you about 1 week to drive there. It's quite far, actually. And on this very surface, the outer crust, the Earth crust, that's where we live, and that's where we get our resources from. And to give you a feeling for scale, you can see the average continental crust of the Earth is about 50 kilometers thick. And the deepest man-made structures are an underground mine in South Africa where they're mining gold. It's about 3.9 kilometers deep. And there is another big mine in the US, in Utah. It's the Bingham Canyon open pit mine. It's about 1.2 kilometers deep. And the deepest ever drilled borehole was done in Russia for scientific purposes. They drilled down to about 12.2 kilometers. So, but I think it gives you a feeling that the mining-related operations, they're just small scratches on the surface of the crust. And more interestingly, if we go deeper into the Earth's crust, we increase the temperature, and we increase the temperature by about 30 degrees per kilometer. And additionally, we also increase the pressure. so the pressure increases by about 300 bars per kilometer. So how much is 300 bars? 300 bars is about 150 times the pressure you have in your car's tire. So it's quite a lot. And if we use this information now, we can go ahead and calculate the temperature and pressure at the depth of about 15 kilometers. And down there we have 450 degrees Celsius and 4.5 kilobars. And that's really hot. So even the Earth starts to sweat. And the Earth's sweat is known also as hydrothermal fluids to geologists. And these hydrothermal fluids are very important because these fluids, they carry important elements and metals with them. In this case, copper and gold. And these fluids, they start to migrate and move up into lower crustal areas. So we need now a process which transports these fluids upper to higher areas into the crust. And this process is actually similar to a thunderstorm. So it's not a normal thunderstorm, it's actually a thunderstorm inside the Earth crust. And most of the people, most of the people in New Zealand, they have already felt these thunderstorms. These thunderstorms are earthquakes. And the driving force for these earthquakes is plate tectonics. So these earthquakes normally occur in very geologically dynamic and active areas. You could think about these areas as the armpits, the sweaty armpits of the Earth. And in these sweaty armpits, we of course produce a lot of fluids, and these fluids, they migrate up into these structures. And additionally, these earthquakes also deform the crust, they deform the rocks, and they lead to screwed up rocks. So we fracture the rocks, we also bend the rocks, and what we get are different structures. Like here, we can see fractures, we can see faults, and we can see faults. And these structures are very important because these structures are able to trap the fluids. And that's where we form economic grade mineralizations or deposits. So it would be quite smart to have a look at these structures in detail. And that's actually what I do in my research with my team. And we are doing structural geology. We measure and analyze structures in rocks. And we are using also traditional tools like a geological compass and a GPS and field boots to get us out into the field. But we also use some new additional tools. One of it is implicit modeling, which allows us to process the big drill hole data sets we get from the mining industries. And a second tool is aerial photography and photogrammetry, which allows us to get a high resolution image of the surface, and we can analyze the structures on these images. So first I want to talk to you about implicit modeling. So I will show you here an open pit of a gold mine, and these are all the drill holes which have been drilled. There are several thousands. They are color-coded by gold concentration, also known as grade. We can now go ahead and spatially interpolate this data, which allows us to highlight areas where we have high-grade gold and areas where we have no gold. So and you can see that the gold in this deposit is not just randomly distributed. It follows a certain structure, it follows a certain trend and has a certain orientation. And that's actually what we do in the research. We go and analyze these geometries and orientations, which allows us to come up with a geological history, and it also allows us to understand this formation process. And with this knowledge, we can then go ahead and predict locations of mineralization in other areas in the world in similar tectonic settings. And as you see here in the pictures, we are able to generate maps which are color-coded by mineralization potential, actually. And this is very helpful for future exploration projects. And second, we also we collect our own high-resolution aerial images using drones or unmanned aerial vehicles and state-of-the-art digital cameras. And then we can go ahead and apply some nifty algorithms like the scale invariant feature transform to these images, which allows us to compute a digital surface model out of these raw images we collect with the drone. Additionally, we can build a texture based on these images, and if we combine the digital surface model and the texture, we are ending up with a 3D photorealistic model of the surface, and we can then go ahead and analyze again the structures, geometry, and distribution of these fractures and faults in there. And as you can see in here, that's a high-resolution image of a coastal outcrop here in Victoria. And you see a lot of lines in there. These are all fractures. And for me, this looks pretty much like a screwed up rock. And this is what we'll still be doing in the future. We'll look further at the Screwedup rocks to ensure future resources for the next generations. Thank you very much.